Welcome to College Algebra, Section 1.2, Graphs of Functions. Part 1, Applications of Piecewise Defined Functions. Here we have a piecewise defined function, which is a function that is defined in pieces, where the expression representing the function is different for different parts of the domain. For this function, a small community has priced water so that consumers who use more will pay more. The monthly flat fee is $20 for usage up to 60 units. Consumers will pay an additional $1.50 for each unit exceeding 60 units, after which they will pay $3 per unit for those units that are over 120. Here is what this function looks like, where C of U is the cost of water in dollars, and U is a unit of water. And in this case, a unit of water is defined as 10,000 gallons. C of U equals 20 for each unit between 0 and 60. C of U is 1.5 U minus 70 for units between 60 and 120, and 3U minus 250 for units over 120. So we're going to verify by using the equation and the graph the following. C of 80, if I look at my graph, here's 80, and it looks like the function value of 80 is about 50. Let's try that. If I find C of 80, I need to use the part of the function that is defined between 60 and 120, because 80 is between 60 and 120. So I have 1.5 times 80 minus 70, which is 1.5 times 80 is 120 minus 70 is 50. And that is what it looked like on the graph. What about C of negative 5? If I look at my graph, negative 5 is not included. That would be about right here. And actually, negative 5 doesn't even make sense in this situation because you're not going to use negative 5 units of water. The smallest amount you could use is 0. So there is no function value for C equals C of negative 5 because the function is not defined there. The last question, why is C of 0 equals 20? So here's C of 0 equals 20. So if you use 0 units of water, why are you paying $20? And the reason is that at 0 units of water, as soon as your house is hooked up to the system, you're paying that $20 fee right off the bat. So that is why C of 0 equals 20. For this piecewise function, we're going to both graph it and write the equation. So during a recent snowstorm, snow began falling in Salt Lake City at 3 a.m. at a constant rate of 1 inch per hour. After 2 hours, the snow stopped for the next 3 hours, and then it started again at a constant rate of 1/2 inch per hour for the next 5 hours. We're going to assume that none of the snow is melting during this time, so whatever snow has already fallen is still there. Let's start by graphing this. So this is the point 0, 0, and let's do hours along the x-axis. So we have hour from 3 a.m., so 1, 2, so hour 1 is at 4 a.m. We're just going to start at hour 1, 4, 5, 6, 7, 8, 9, 10. And then we'll do inches on the left side of the graph along the y-axis. So we'll start with 1 inch, 2, 3, 4, 5, 6, 7, and 8. So at the beginning, we're starting with no snow at the beginning. And then the snow is falling at a rate of 1 inch per hour for 2 hours. So 1 inch for the first hour, another inch for the second hour. So after 2 hours, we have 2 inches of snow. So that's the first part of the graph. To write the function for that part, we have 1 inch per hour. So our slope is 1 times the number of hours. And this is when our x is between 0 and 2. So that's the first part of our function. Let's look at the next part. After 2 hours, the snow stopped for the next 3 hours. So for the next 3 hours, no snow is falling. So from hours 2 to 5, we don't have any snow falling. It's staying at 2 inches. So our function for that whole interval is 2. And then after that, the snow is going to fall at a rate of 1/2 inch per hour for the next 5 hours. So if 1/2 inch per hour, then in 2 hours, it will fall in 1 inch. So after another 2 hours, we fall in 1 inch. After another 2 hours after that, we fall in another inch. And then for this last hour here, we fell in 1/2 inch. So there's our graph for that last part. So that part is when 5 is less than or equal to x is less than or equal to 10. We need to figure out what that equation looks like. So the equation for that part, we have 1/2 inch per hour. And we need to find that y-intercept. If I was to keep graphing here, where would my y-intercept be? It's hard to tell on the graph because my graph is not perfect because it's a hand-drawn graph. So I'm going to instead say, okay, if I know that f of x is 0.05 or 0.5x plus b, and I also know a point on that graph, I'm going to use this point right here that is the 0.52. If I plug in 5 for x and 2 for y, so I have 2 equals 0.5 times 5, because x is 5 at that point. I'm just plugging in one of the points on the line, and this looked like the easiest point to plug in. So I have 2 equals 2.5 plus b, and if I subtract 2.5 from both sides, I have b as 0.5. Sorry, negative 0.5. So my equation will be 0.5x minus 0.5. So there is my piecewise function. I have it graphed and I have the equation written. Now let's look at the last question. What are the applied domain and range? That means in this context, what are the domain and range? So the domain in this context is 10 hours, from hour 0 to hour 10. So we've accounted for all 10 of those hours, and we can see that on the graph. The range of this function, we started at 0 snow, so 0 inches of snow, no snow. And if I look at my graph and think about what I've talked about here, I can see we end at 4.5. So my range ends at 4.5 inches of snow.